Otherwise, we're going to get started. Let me look this out so I know what time. Well, it's actually running ahead by me a little bit. That's interesting. Okay. All right. Welcome to lecture. Again, we have a little bit of an unfortunate situation going on with the camera. So move over here if you'd like. Remember that we have an exam next Monday. We don't normally meet for class on Mondays, but we will have an examination. Okay. So be prepared for that. Today is the last lecture that will be present on that midterm. So today's content is fair game. Next lecture's content is not. Okay, you might have gotten that impression. Okay, so pay attention today, and then next week or next lecture, don't pay attention. No, I'm kidding. Okay. One thing also I noticed is that in the quizzes I give out, there's a password, and if you looked at how I put it online, I put like a left bracket, right bracket, obfuscated, which means like hidden. And some people have been submitting quizzes with the passcode as obfuscated. I don't know whether or not this is the person that's actually in the lecture. If you're in the lecture, put the one on the board. That's the actual password. And if you're not in lecture, don't bother because it's not the right password, and we'll know that you're not in lecture, I guess. But it's for completion points anyways. It doesn't really matter. So well, I guess it does kind of matter. So just a little funny note there. So I talked about the exam. House points. Blue team is still looking strong, I gotta say. I've decided I'm probably just going to reset your points after the first boba date, just to keep things fair so that one house isn't in the lead the whole time. So sucks if you're in blue team, I guess. But it's still anyone's game, I believe. Someone can pull it back. Okay. So hello, functional programmers. Today we're talking about sorting and parallelism. Last lecture we talked about work and span. This leading into this idea of mathematically proving the runtime of certain functions in SML. And today we'll be talking more a bit about parallelism or span. What do we do when we have infinitely many processors? Okay. So there's 4 things we're going to talk about today, which are a new method of analyzing trees. Instead of doing the number of nodes, we're going to talk about the depth of the tree. We're going to use a method called the tree method that you should have learned in your Friday lab. We'll go more into detail on that. We're going to write inord, but better, and then we're going to get into sorting. I have a lot of content to go through this lecture, actually, so we should probably get rolling. But yes. Okay, so we talked about asymptotic analysis, talked about big O notation. This should have been a review for most of you, but hopefully we have a better foundation for thinking about it. And we learned that for functional programs that are recursive, we can write recurrences to measure the runtime, because predictably, for a given input size, we can always get the same abstract cost out. Not the same exact cost because we're agnostic to things like hardware, but we can get the same approximate cost in abstract units like C sub 1, C sub 2, unknown constants that are not known to us a priori. Okay, and then we can use the unrolling method to solve those because we use expand it once, expand it twice, get a closed form, and then solve. And you can refer to the last lecture if you don't remember that exactly. And then we also learned that if we have infinitely many processors, we can do recurrences that take the max over the longest path. And what I mean by that is when you have tuples, the computations in the tuple can be done in parallel, meaning that we can take the max over how long it takes rather than summing them. Okay? Is everyone so comfortable with that idea? Because we'll make use of that today. Cool. All right. Let's talk about analyzing a tree via depth. In particular, it's going to be that function right there, but let me see if I have something to say. Oh, I can't look over there now. So we talked about how the number of nodes in a tree is going to be our measure of the input size. And remember, we always have an input size. So O of n is going to be our number of nodes, and then we got the O of n bound and imbalanced, and then log n in the balanced case in the last lecture. But we can also measure it via the depth. So there's an idea of both the nodes and the depth. So nodes or depth are both perfectly valid ways to solve recurrences. All right, and we're going to solve one right now. So here's tree sum. Let's do the span recurrence, but now for the unbalanced case, but in terms of the depth. So where D is the depth of the tree, and if you forget what the function says, it's up there. Tree. Okay, so let's do tree sum. S sub tree sum. And what's my first move? What's this? So remember that this is now D, but does my answer change? I still have a constant amount of work, or span, so I'm going to do this. I'm going to say C sub 0, and now I'm going to move into S sub tree sum of D, okay? And I'm going to tell you that S sub tree sum of D, well, what am I going to do? I'm going to take the max over these 3 things, right? Okay, so I'm going to make a 3-place tuple, or a 3-place max function to indicate that to you. So I take the max over S sub tree sum of whatever the depth of the left subtree is, comma, like some constant value, and then the span of the right depth, and then plus some constant amount of work. And you should be comfortable with this idea because this is corresponding to the call to tree sum L. This is the x. We have some constant amount of work allocated to it. And this is tree sum of R. Does this make sense to everyone? Why we have three things in our max? It doesn't really matter. I drifted a little bit, I see. And then afterwards, we sum up the results so we have some constant amount of work. But what is the depth of the left and right subtree in the unbalanced case? So if I have a tree which looks like this, what is the depth of my left subtree, let's say, if it's a left spline? D minus 1, yes. So what I'm going to say is I'm going to replace the D minus 1, and then my right subtree is necessarily like 0, okay? And if we take the max over this, you should believe me that this is the maximum. So we're going to get S sub tree sum of D minus 1 plus C sub 2, okay? And then how do we solve this? Well, doesn't this look pretty familiar, right? Haven't we seen a recurrence like this, except we just swap out the D for the N, right? So in this case, this is similar to when we got a recurrence in N, which was S of, or W of N minus 1 plus a constant amount. We're going to do this D many times, and we're going to get a constant out each time. So do you believe me if I skip ahead and then say this is O of D? Is everyone familiar with that? I'm going to skip some of the calculations we have already done in favor of getting to more calculations we haven't done so I can show you in lecture right now, okay? But this is O of D, all right? So that's the unbalanced case. I removed the implementation, but it's fine. You should know it, and it's on the board. Let's do S sub tree sum. So where D is the depth of the tree, and then now let's write balanced. And this computer will do that occasionally. I can keep it warm. I can just go like oop, doop, doop, doop. Okay, S sub tree sum. And I'm going to write the base case, even though strictly speaking, you all should be familiar with that. And now let's do the D case. Okay, in the balanced case of a tree, I've got something which looks like this, right? Well, I'm going to have pretty much something of the same form as this actually, right? Because the configuration of the tree just decides the D sub L and the D sub R quantities. It doesn't change the form of the recurrence otherwise. So can someone tell me actually what's the depth of the left and right subtrees? Over 2? Does my depth of my tree go down by 2 when I look at the left subtree? Minus 1. My depth of my left subtree is 1 less than the depth of the whole tree. I'm going to write this whole thing out just to be super clear about it. S sub tree sum D minus 1. And some of your spidey senses may be going off and it feels weird, but trust me, this is the right way to go about it. And we'll explain why, okay? So then if I take the max, these two quantities are the same. So I'm going to just produce one of them. S sub tree sum D minus 1 plus C sub 1. Or C sub 2, actually, I should change this to. Just so I have all my ducks in a row. Okay. And then do you believe me again, this is exactly the same thing. So now we get O of D again. Okay. But what's going on here, right? Because we know that tree sum is a function that should get a parallel speed up, right? Because it has 2 recursive calls. I can clearly do both of them at the same time. Like, why did I get the same bound of O of D for my work and my span, or sorry, for my unbalanced and balanced cases? That's kind of strange. So let me tell you that the reason for this is because depth is relative, okay? We're going to find that this is actually the right way to do it. And we can go through this, and this is basically the same stuff. But this is the same recurrence. Span is both O of D. It's counterintuitive, but remember the task dependency graphs, right? If I look at this tree, and I think of it as a task dependency graph, I can't really reach this without looking at this, and I can't really reach these without looking at this, right? I kind of have that data dependency in the literal structure of the tree. So it kind of makes sense that, like, if I'm doing this, right, if I'm doing the work of the span, I can kind of just like go through each level. It doesn't really matter. I should always have gotten O of D because I just go through each level. It doesn't matter because all these can be done in parallel. The difference comes in how you look at the relationship in the balanced and unbalanced cases for the depth of the tree. So let's look at this, right? Previously, we got O of n and O of log n. I'll tell you that for the work of tree sum, or sorry, for the span of tree sum in terms of depth and nodes, right? So we ended up getting a better bound because we got log of n. here's what's going to happen. Here's the fact that you need to know. In an unbalanced tree, which is this guy right here, the depth is just the number of nodes, isn't it? This is just the number of nodes because I'm a left spine. The number of nodes I have in an unbalanced tree must be the same. So that means that, so because n is equal to d, I'm going to get that this is just O of n. And you might not recall exactly, but this was the bound we got for tree sum in the nodes case for my span, for the unbalanced case. This was O of n, okay? So this is the same bound if you translate the fact that depth means something different in an unbalanced tree. Or alternatively, in a full tree, in a complete tree, this guy, my depth, how does my depth d relate to the number of nodes I have in this tree? Does anyone have a guess? How is it related? Shout it out. Well, did I say how the nodes are related to the depth or how the depth is related to the nodes? 2 to the d, right? We have roughly, okay, so let's see it this way actually. So level I nodes, right? This is level I equals 0, I equals 1, I equals 2, so on and so forth, right? So if I want to find the number of nodes in this tree, and this is also just a math fact, but I'm deriving it in front of you. If I want to find the number of nodes in this tree, I'm going to do 2 to the 0, plus 2 to the 1, plus 2 to the 2, plus dot, 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 until I get to the very end, which is d. So that's plus 2 to the d. So this looks like 1 plus 2 plus 4 plus dot, 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 plus 2 to the d. And here's a handy math fact for you. That is going to be on order of 2 to the d. I'll just write that to you in a second here, okay? But that's a math fact, which means that O of d here, well, my depth is, so let's see. Well, n is equal to 2 to the d, right? So then if I do this out, I'm going to have log n is equal to d. So then if d is log n, is this not true? Does everyone see how this came about? And I'm gonna, this is a suffice to show, okay? We assume this, we get that result. Now I'm gonna show you why this is the case, okay? But it's because if I sum this, it's order of d, or 2 to the d, assuming n is equal to 2 to the d, log n is equal to d if I take log on both sides, and then that equation means that d is log n. Is everyone cool with this? I'm just reiterating that because I feel like I want to make sure people are following. Okay, cool. Let's talk about why that is, as soon as the computer wants to wake up. Okay, so here's the idea. There's a very nice geometric proof I'm a big fan of that shows that this is just the order of the largest thing, okay? I'm a big fan of this proof. So I think it's very pretty. So I'm going to draw out for you. Suppose I have a square. What's it called? A platonic shape. So this is n. Suppose that half is n. And then if I cut this in half, well, this is a half of that, right? So it's n over 2. And this is n over 2. So if I cut that in half, isn't this n over 4? And then if I cut that in half, isn't this n over 8? And if I cut, you get the point, right? So the continuous sum of n and n over 2 and n over 4, if I keep summing halves of that thing, the area of these squares, of these rectangles, never eclipses the size of the square. And what's the size of the square if this is n? 2n. And that's if I do the infinite sum. Okay, I converge to 2n. If I do the finite sum, which, obviously, this is, because I start at 1, I don't keep going to 0.5 and 0.25 and so on and so forth. If this is the finite sum, this is strictly less than that infinite sum. So this is definitely upper bounded by the largest one. I realize this is 2 to the d and that's 2n, but realize I just mean like the sum of successively doubling things is on the order of the largest thing. It's going to be, in fact, equal upper bounded by 2 of the upperest thing. But we care about upper bounds. We care about big O. Does everyone follow why that's true? You should be able to, if you're ever confused, like draw this square in your head and just remember that that left thing is n, and then you should be able to rederive this fact whenever you need to. Okay? Think like a physics major. Rederive. All right? So that's true. Okay? So we get log n. So by doing it via depth, we get just the same calculation as we would have gotten with nodes. It's just that depth means something different here. So it looks different, but if you think about it, it's not. So it's just a different way of doing the same thing. Okay? And arguably, one might be easier than the other, but usually on an examination, and when I say usually, I mean on your examination next Monday, we will specify which one we'd like you to do. I will say, if you want to do this, like do the span, in the unbalanced case, in the number of nodes n, so on and so forth. Okay, is everyone cool with this? 2 span calculations. Okay, that's just a different way of doing it, all right? And this is just all the justification I just showed you. I have a nice little text square right there for you. Okay. So this is going to be our complexity table for tree sum. Yes? I'm going to erase this. Yes, that is what I mean. It doesn't, in the asymptotic case, it actually doesn't matter if it's perfectly balanced. Like, it could be like approximately balanced, which is to say that like the number of nodes in the left and right subtrees are on the same asymptotic order, or they could be plus or minus 1, or it could be a constant factor. Like, it doesn't actually matter. But like, for simplicity, let's assume a balanced tree is a complete tree, a full tree, a happy tree, if you will. I'm not Bob Ross. Okay, so these are the complexity bounds we get. All right, is everyone clear on this? This is nodes versus depth in the balanced and unbalanced case. Yeah. I mean in the entire tree. When I say n, I generally mean the number of nodes in the entire tree, but that's an important distinction, yeah. Sorry, when you say d plus 1, 2 to the d plus 1. Yeah. So another fun fact about binary trees is that the number of leaves at the very bottom is going to be like almost exact, like the upper bound. It'll be like half of all of the nodes in the tree. Binary trees get big exponents. 2 to the d plus 1 would have been a better thing to say, yeah. Very true for that. Cool. Okay, let's move on if everyone is on board with this, because we're going to talk about inord, all right? Cool. We're going to talk about the tree method. Everyone here is familiar with the tree method. You saw it in Friday's lab, right? I see stoned faces, but I'm pretty sure you did. Okay. Is it that you didn't see it, you didn't go to the lab, or you didn't understand it? It's hard to give a trinary answer via just like raising your hand. So let's assume that you said you just saw and didn't understand it. Cool. Okay. We talked about traversals on a tree last. Wait, is that a question? No, it's not. We talked about traversals on a tree some lectures ago. We talked about inord specifically. Let's talk about inord again. And who would have it? The implementation is right up there for you. Okay. This is the definition of an inord traversal. It's left root right. Okay. We're going to try and analyze the work in span, and we're going to do better. We're going to try and get through the work in span in the balanced and unbalanced cases. 4 cases for us. Okay. So let's get started on that. Let's try it out. Let's do the balanced work case. Okay. We're just going to try and do this because we can. All right. We're going to try and see what we get, and we're going to find that it's not that great, because I guess my motivation to you is if you ever see an append where you're feeding into the append results of your recursive call, you should think something fishy is going on. You should, in the words of another professor in this department, you should check your wallet. Right? Something's going on. Right? Someone's trying to have their way, and you shouldn't let that happen. So I'm going to tell you right now, this is not going to end up well for us. So let's do it. W sub inord, and let me actually preface again. Actually, for everything, it's going to be where n is the length of the input list, number of nodes. Oh. Input tree, okay? Always write that before you start, and then we're going to get started. This will hold in every case. I'm going to write out the base cases, even though by all rights I should stop doing that. All right. So we're going to strictly do this via nodes. I showed you how to do depth, but we're going to throw that to the side for a second and not care about it, right? If I've got W sub inord, what do I have here? I've got 3 things that can be done in parallel, right? I can do the inord L, I can do the inord R, and I can just have the X, I guess. I can't do the append yet, right? Because the append depends upon the results of the inord and the cons and so on and so forth, right? So the append will be strictly sequential. It's the last thing I do. It's when I collect all of my results, okay? I should turn that off, but that's okay. Okay, so based on that, can someone give me an idea for what this recurrence should look like? What am I going to write here? How many calls do I have? What's my work? Yeah. Yep, we're skipping that a bit, but that's pretty much the idea. Let's see, which parts of that do I want to simplify immediately? So let's write this out, okay? I'm going to stage this a little bit more. So absolutely right, we have two calls to inord on the number of nodes on the right and the left. I'm going to write this once, and then I'm going to assume you get the hint from here on out. When I have the W, actually, I'll write this out too. I'm going to do this. W sub append, where the number of nodes here is going to be roughly equal to L, right, n sub L again, plus C sub 2, C sub 1. Okay, number of nodes on the left, number of nodes on the right, right? Because append, remember, is linear in the length of the left list, right? So I don't care about the right list at all. So I only care about n sub L. And as Stephen identified, we only have, in the balance case, n over 2. So let's replace, shall we? So this is otherwise known as 2w sub inord n over 2 plus, and let's replace this with like some abstract units. I feel like I'm going to talk a little bit about that in a second. Okay. I claim that this is the normal form, like the canonical form for what we're going to use to simplify, okay? Because I got n over 2 abstract units from this O of n append call, and then I just simplify these because there's 2 of them, right? And then that's a constant amount of work because there's always a constant amount of work. Is this contentious for anyone? And by contentious, we mean not good. Cool, awesome. Let's solve this. But if we try to solve it, something's going to happen here. So this is the same thing as we just got, right? But we're going to do this, and we're going to arrange it. I put O of n here instead of abstract units. But basically, if we unpack this W sub inord, we're going to get 2 times this guy, which is itself 2 times. So it'll be, if we expand that now, it's 2 times that. Oh, it looks a little bad. I don't like this, right? Because now we're not getting 1 term per unrolling. We're getting like 2 to the I terms per unrolling. So let's do it via the tree method, all right? So someone restate the tree method for me. What do I do? What do I do in the tree method? Testing your knowledge. Yes. I like that, yeah. Nodes, yes, nodes per level, right. The idea is that we can partition our recurrence, we can partition our calls via the levels of the tree. I'm not going to draw this out because I have a very nice pictures for you. But the tree method basically looks like this. We have a tree representing the computation of inord of t, okay? The top node indicates the call to W sub inord, or the call to inord on a tree of size n. And that call itself branches out to 2 calls on inord, right, again, on trees of size n over 2. So that's what this graph looks like. And let's iterate that process. Let's keep doing it. So n over 2 calls n over 4 twice, and then we keep on keeping on until eventually we reach 0, like some number of times. I'm not going to draw out all of them because I can't also, it's not fixed. So this is like what we call our computation tree of the tree method, okay? And then based on this, we're going to partition by each level to try and see whether or not if we find a pattern over the sum of all the levels, it is easier to solve. Ideally, the amount of work on each level should be constant. That'll be the ideal, right? Because then we can just multiply by the number of nodes, or sorry, the number of levels, and then we just get our bound. Does that make sense? But sometimes it's not always the case. So let's do it out. There are 3 parts to a recurrence, right? As I forget your name. Arnav. As Arnav identified, we have 3 parts. We got this. I startled you a bit. I'm sorry. You were chewing your high chew. The input size, which is in green, you might not be able to see. And then we have the non-recursive work, which is in a vague kind of faux purple. And then we have the recursive work, which is red. Red meaning don't worry about it. Because the red is induced by your children. If we can count the non-recursive work at each node, and the recursive work is denoted by just the subtree here, then if we just sum all of the non-recursive work, we should get the work in total, right? So we're just going to worry about the non-recursive work here. So our non-recursive work here is going to be this quantity, right, which is this, n over 2 c sub 2 plus c sub 1, which is linear in n. So we have that non-recursive work. We have the recursive work, which I told you don't worry about. And then I have an input size, which in this case is fixed at n, but will change throughout each level of the tree, okay? So yes, and so my claim to you again is if we sum all of the non-recursive work in each node, we will get the work by the entire function. Does that make sense to everyone? Is that a true statement to everyone's brain? Okay, cool, awesome. Let's do it. So we're gonna have to figure out the recursive work done by each node, which is not super easy to do, but we'll try. So I showed you again that this tree looks like this. And this calls n over 4 twice. But remember that the amount of work we do at each node is itself dependent on the level, right? So okay, there are 3 quantities we're interested in. We're interested in levels, nodes at level I, and we're interested in work per node at level I. So like work per node, like this guy at level I, level 1, 0, and 2. Nodes per level, so the number of things per level, and then the levels, which is the height of the tree. Okay? And remember, this is all supposed to be in terms of n, the number of nodes in our tree in particular. Okay? So how many levels do I have? If I have a tree of n nodes, how many levels? Shout it out. Log n. I like it. Log 2 sub n. Yeah, log n, asymptotically. Doesn't matter. Nodes at level I. Well, hint, level 0's got 1. Level 1's got 2. What does that sound like? It sounds like we're doubling each time. 2 to the I, right? And then the work per node at level I, that's a little more unclear, right? So, well, let's see. So if I'm at level I, I've got a size of, so here it's going to be n over 2 to the I, right? That's my size at a given level. So size, let me actually say, let me give you a different quantity. Size at level I is n over 2 to the I. Does that make sense? Because at the 0th level, yes, that's true. Because I have n over 2 here at the 0th level. At the next level, it's going to, this n over 2 is going to substitute, and we'll get n over 4 c sub 2, and then n over 8 c sub 2. So the amount of work, the size of my input is going to be just keeping dividing by 2. But the amount of work I do is, actually, sorry. I meant the amount of recursive work, yeah. Does that follow? Because if I have level 0, oh no, wait, I was right the first time. -1, oh wait. Oh, sorry. So, okay, let me actually go to the tree I happily drew for myself. Here it is. I wanted to avoid drawing this out, or I wanted to avoid showing you this because I wanted to draw it out on the board. But let's just do it. So, does everyone follow this encoding that I'm showing you here? If I have the green, that's the size at the given node. So I have n over n, and then n over 2, n over 4, up until 0. If I have the purple, that's the non-recursive work done at each node, right? So at the first level, it's c sub 2 times n over 2. Then at each level below that, it divides by 2 yet again, right? Because I'm dividing the input by 2, and this is linear in that. This is linear in the constantly having input, or the constantly having size. So here it's c sub 2 by an n over 2 factor, c sub 2 by an n over 4 factor, and at the base case, remember that we have w sub 0 is going to be c naught. So these are all technically c naught terms. Does everyone follow this? Okay, I'm not going to ask. Thumbs up, thumbs down, and or to the side. Okay. Okay, I saw. Okay, yeah. So if we sum up everything that's done by each level, the purple quantities at each level, we should then be able to sum that way and then get the whole thing, right? So if I had just the sum here, that's going to be 2 to the 0 because the number of nodes multiplied by the non-recursive work done at each node will be the work at level I. So 2 to the 0 nodes multiplied by the non-recursive work at that node, which is c sub 2 times n over 2, is, these are supposed to be 2's, don't worry about it, c sub 2 times n over 2. And then I have 2 nodes at level 1, which means 2 to the 1, because that's how many nodes I have via this thing. So that's the number of nodes multiplied by c sub 2 by n over, multiplied by n over 4, because I divided by 2 again, because of this thing, right? Which is actually going to be, yeah, n over 2 to the I, actually, c sub 2. Yes, okay. So if I just multiply these two quantities, I should just get out what that is, right? So I'm going to get n over 2 each time. Every single time I get c sub 2 times n over 2, because I'm canceling these out, right? I'm gonna get that right quantity. I'm gonna get the n over 2 multiplied by c sub 2. Is everyone clear on that? Like these things kind of cancel out. Oh my goodness. Invest in airfare. Okay. And then what's the number of nodes I have, or the number of levels I have? Well, that's just log n. So if I multiply the constant amount at each level by that, so I get c sub 2 multiplied by n over 2 multiplied by log n, which is work at level I, and then height, depth. Well, then what should I get here? What does this look like asymptotically to you? N log n. A few things to note, which is, one, I kind of dropped this, the c sub 1, because the c sub 1 is asymptotically dominated by this. So I kind of like stopped thinking about it because I didn't care. We're allowed to do things like that so long as we're assured that like asymptotically it's equivalent, and we're not making too big of assumptions, because asymptotically I could also like, well, okay, asymptotically equivalent is fine. So that this absorbs into that. Secondly, what I did is I ignored all these guys at the bottom. It's true there's a lot of them. There's actually roughly like n of them, n over 2 of them. But that's a constant amount, which means that this is just going to be a linear term, which means that it's greatly overshadowed by the sum of every other level above it, because that's going to be n log n. So I absorbed both the constants here, and I absorbed the linear term induced by my leaves. Does everyone see why this is the case? I'm going to keep asking that. I feel like I'm going to be really annoying about it, but I want to make sure people are following. Any questions? Yeah. Yeah, so the C1 I think I just misplaced because I bind and replaced, but it only does the first one per line, so I didn't get the C sub 1. So this C sub 1 probably shouldn't be there. Yeah, it shouldn't be there. This, you asked about the difference between C sub 2 and C sub 0. Yeah, so it's the original C sub 0 and C sub 2 here. This C sub 0 is the amount of constant work done at each leaf, every time that I have an empty tree. And C sub 2 is a term that we get linear in my input size at each node. So those are the two main things determining my complexity. I'm actually gonna keep doing this. All right. Okay. Does everyone have this like image etched into their brain? Because you should see this when you should see this when you sleep. You should see this when you shower. When you close your eyes, it should be tattooed on the back of your eyelids. Okay. If you're ever confused about complexity, re-derive by drawing a tree. The TAs will enjoy it, in fact, if they grade your papers and they see a bunch of trees drawn everywhere. Like, this guy's a tree fiend. No, it's just, you're doing the tree method, all right? So, tree method, tree picture. It'll help you, okay? And beyond that, also this is the important thing, okay? Levels, nodes at level I, work per node at level I as a function of the size at level I, okay? Usually this will be a function of the size at level I, okay? It doesn't always need to be. We'll see examples where it's not true. Everyone cool to move on? Any other questions? Yeah. Yeah, so if you look at the sum of all these guys, which is 2 to the 1 times c sub 2 times n over 4, or 2 to the 2 times c sub 2 times n over 8, it always sums to this right thing here, which is c sub 2, which is a typo, times n over 2. So I'm just taking the work at level I, irrespective of nodes. Yeah. Oh, yeah. Sorry, why is the work at the non-recursive? Repeat that? Oh, this. Yeah, this is because we previously proved the complexity of append, and we know it's linear in, yes, okay, cool. It's linear in the size of the left list, right? You could replace it by n. I'm being a little strict here. If you replace this with n or even O of n, honestly, I think that would be fine. But I'm being rigorous for the sake of it, so that you see where the constants are coming from. Yeah. Yes, when I have L append R, we did this actually previously, but the complexity of L append R is only dependent on the size of L. This is a balanced tree, so I get to do that. Okay. Sorry, yes, we're doing. All right, who wants to volunteer to touch this for the rest of the lecture? That's a joke, don't do that. All right. Okay, let's move on. That's one case. So let's pencil it in. Let's put it in our little bag of tricks. So work of the balanced case is going to be O of n log n. Is everyone cool with that? Everyone remember how we did it? Like exactly 5 minutes ago? Cool. Let's move on. We're going to try and get through some others, okay? Okay, so now that we've done the balanced case for inord, let's try to think about the span for the balanced case, okay? We're going to do it analogously, right? So if I've got the span of inord on a balanced tree, so we're going to say balanced span, I'm going to stop writing out the base cases, okay? You can assume that's 0 equals C sub 0, all right? Let's do S sub inord. And also, this applies to everything, okay? It's always going to be the number of nodes. So I'm omitting writing that for brevity. Well, what's my implementation say? My implementation says that I need to do, well, actually, I don't have my implementation anymore. Oh, man. All right. If you remember, my implementation looks like this. It's easier for me to just write it. Cool? If I have these many things, I can parallelize all of these guys, right? So I'm going to do that. So instead of having what we had here, where we had 2 of W sub inord, well, I can actually just take the exact same recurrence, but instead of adding these 3 quantities, I'm going to take the max. And I'm not going to explicitly do it out, but if you go through the math, you're going to find that it's 1 call to n over 2, such that I get plus this append that happens afterwards, because that's not part of the max. So I get S sub append of n over 2 plus C sub 1. And then this itself is just going to be S sub inord of n over 2 plus n over 2 C sub 2 plus C sub 1. Is everyone clear on this? We get exactly the same thing, but now we can parallelize both of our calls. And now we can use the unrolling method. We don't need a sinking tree method. Actually, the tree method is generalized. You can do it if you have only one recursive call too. But if we do the unrolling, we're going to get S sub inord of n over 4 plus n over 2, n over 4 C sub 2 plus C sub 1 plus n over 2 C sub 2 plus C sub 1, right? Because I got this out. Because previously I got this out. And this just looks like the sum of what? If I iterate this process, how many times can I do it? How many times can I divide by 2? Log. So I'm going to get the sum from I equals 1 to log n. And then at each time, I'm going to get something dependent on my size. What is it? It's going to be a fraction in n. N over 2 to the I. 2 to the I, probably plus 1, honestly. Doesn't really matter. Let's just say plus 1. C sub 2. Actually, no. Let's just simplify it to 2 sub to the I. We don't need to be super rigorous about it. We're trying to get the math right here. Okay. So we get this sum, which looks like the sum of halves again, like 1 and then 2 and then 4. What did I say that was? 2 times whatever this is, right? The biggest term, which is linear. So we say that this is, so we say math, and we get O of n. I want that to show up, okay? So we get linear. Does that make sense to everyone? Because we took the span of inord, and we can parallelize it, so we have some calls going on in parallel. Seems pretty good to me. Oops, jeez. Oh, jeez. Sorry. Okay. Yeah. Yeah. So I skipped over it a little bit, but basically, because if you let's look at the implementation first. This is our recursive call, right? I omitted the rest of the function, but this expression is what we evaluate to. So we take inord L, append to this thing where we also compute inord R. If these are all tuples, because this is a tuple, and this is a tuple, because infix functions take in their inputs as tuples, okay? If you have an infix function, you can always parallelize the left and the right. Then these two can be done in parallel, inord L and inord R. So if I take the max over them, I only get one call to S sub inord of n over 2. Okay, all right. All right, everyone cool on this? We have O of n. That was not as bad as the previous one, right? All right, that's only because we've been assuming that the world is fair. So we're going to assume that the world gives us fair, balanced data. And it turns out, by the way, that's not true, okay? So let's do unbalanced for the work. See what I did there? Okay, so does anyone have a hypothesis for what we should do? What is the worst case for our input if we have the work of an unbalanced tree for inord? And let's actually move ahead a bit because, oh geez. I want to see if I give you the implementation again. Here we go. Okay, span of a balanced tree. We already did that. We're not going to do span of a balanced tree. We're just looking at the implementation. Okay. Okay. Yeah, it is, but I'm keeping it up because I want the implementation. Cool. So unbalanced work case, W sub inord of n hit me. What am I going to do? So what is the worst case for me? Now L and R could be any quantity so long as both sum to n. What is the worst case for me? Just thinking about it. Don't think about the math yet. Yeah. To the left. Why the left? You only append the left, and left is linear in the left tree, right? So a huge spine to the left is going to be our worst case. So yeah, the real secret I'm going to reveal to you at the end of the semester is I've been slowly, like, casually missing these on purpose. It's so I make you reach for it, so I can make sure you're awake. That's not true. So we're going to have a giant spine to the left. So n sub L is going to be n minus 1, right? And then n sub R is going to be 0. So we're going to do, I'm not going to write it out. I will write it out. N minus 1 plus W sub inord of 0 plus, I'm going to write out just this, okay? Actually, no, sorry. No, this is important. Does this make sense for everyone? Because my W sub append is appending that guy, which is of length n minus 1, if there are n minus 1 nodes on the left. So what do I get? Let's just like absorb this into our constant. I don't care about it because this is like C sub 0. Okay, so this is going to be part of C sub 1 from now on. So we're going to do W sub inord n minus 1 plus n minus 1 C sub 2 plus C sub 1. Okay, because this goes to that, and then I absorbed this quantity into that. Okay. Okay. Is everyone on board with this? Well, what does this look like? We have one recursive call, so let's unroll. We're going to say, I'm going to move to the left here a bit. N minus 2 plus n minus 2 C sub 2 plus C sub 1 plus n minus 1 C sub 2 plus C sub 1. Let's just leave it. I'm getting an n minus I term each time. So if I write out the summation, well, I'm going to be doing this n minus thing n times. I equals 1 n. And I'm going to have n minus I C sub 2 plus C sub 1 plus C sub 0. Does everyone see how this goes to that? I'm summing over the amount of times I unroll. And I always get one of these out, and I always get one of these out. Okay? Turns out this is not going to matter for us asymptotically, but let's care about this. What does that look like? Well, it looks like 1 plus 2 plus dot 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 plus n minus 1 C sub 2. Yes. And then the rest doesn't really matter. What is this again? Oh, wait, sorry. Oh, yeah, that's true. Yeah. Let me clarify. Plus 3. That's important. Okay. It's not doubling. It's incrementing by 1. What is the sum of the first n minus 1 numbers? Yeah. N squared. Yes. Okay. That's what I wanted to hear. Yeah, I decided to include it. I include and don't include things based on my mood. Honestly, like if you omitted, well, I think it'll be fine. Like
we should include C.
I think it's annoying personally. I think it's fine too. I think it's fine not to include because the base case is pretty much never going to matter asymptotically. At least in this class, I think. Yeah, so it's annoying. So I included it for the sake of completeness, but I think it's fine if you omit it as well. So we're gonna get O of n squared. Okay. Yes. Yes, I can. Thank you for asking. You get a high tree for that. Whoops. Thanks. Yeah. So that's an interesting question because the nodes are like the recursive nodes, but you could have non-recursive work that could itself be parallelized. Like suppose, so I skipped over this maybe a little bit, but also maybe I didn't, which is S sub append. And I skipped over, oh yeah, the span of append is the same as the work if you were confused as to where this came from. But the span of append, like imagine this wasn't append, but it was a function that had like an actually good span. We would actually get a different bound, even if we couldn't parallelize these calls to inord. Does that make sense? Like we might rely on a helper function that has a good span, a different span, even though we can't parallelize the recursive calls. So when I say like 2 nodes in the tree, realize that this tree I'm inducing is just my recursion tree. but the non-recursive work can be parallelized too. That's the idea, right? Does that make sense for everyone? The non-recursive work can be parallelized too is the idea, okay? Yeah, good question. A Lannister pays his debts. All right, okay. I never even watched that show. Okay, n squared, okay? So let's write it down in our handy fact machine. And what we're going to find actually is, well, let's think through the span case for unbalanced, right? Well, if I have the span case for unbalanced, I'm going to similarly get that this is span and span, but now they can be parallelized, except that this is still really big. This is still the max. So I still get out this term. So let me concretize what I mean, okay? It's like, if I wanted to write this, right, I would get this, but it wouldn't be n over 2 anymore. The max of this is going to be n minus 1. Right? Do you agree with me that this is the unbalanced span case? That my left tree is still really big. That's still the worst case for me. And I can parallelize, but it doesn't really matter, because I'm parallelizing doing S sub inord on 0, which is really, really like not important at the end of the day. And then isn't this recurrence the same as that one, if you look at it closely, which is W sub inord n minus 1, S sub inord n minus 1, n minus 1 C sub 2. Actually, sorry, this is n minus 1 as well. Right? These look the same, right? So I'm actually going to tell you that like outright, like the span is going to be the same in the unbalanced case. So I'm not going to bother to do out the work. I will leave that as an exercise to the lecture watcher. All right. Is everyone cool with this? All right. Yeah. It is not n to the n. You would find it difficult to. Some people would not find it difficult to write a sort that's n to the n. Okay. I hope all of you would. I have faith. All right. But like, yeah, we don't quite want that. Good call. Good catch. All right. This is our table. This is the complexity of inord. We worked through all the cases moderately. Okay. And I believe that's break actually. And by break, I mean ask questions. I will take questions now via Menti or aloud. All right, before we move on to the next part. Yeah. That wasn't a question, but I'll take it anyways. All right, maybe. I would like to read a book series that finishes before like ever, because GRRM is going to die. But yes, yeah. When did this become like an AMA? Like I was asking for content questions. Like this is my lecture. Come on. No, I don't know what that is actually. Okay. Any other questions allowed that people have? We'll have a quiz right after this, by the way, so don't leave. Okay, someone left, but that's okay. Okay. I'm going to check really fast if we have any Menti questions, and then why are functions pointers? They aren't. Let's see. Can I get a haichu? It's an anonymous question. What do you want me to do? Give one to each person in the room? Put your hand up if you want a haichu. Like, yeah, this isn't clear at all. It's all of you. All right, quiz time. Sounds like most people are pretty much done. All right, let's get rolling. We got some stuff to cover still. I promise you we'd get to implementing merge sort. I said 15 lines, generously spaced. I lied, 20, but it's fine. But I really want to get to it. But first, I wanted to say something about inord. So I erased it here already, but we got like a bunch of random stuff like n squared, or n log n, n squared of n. But I wanted to talk about how we can do that better, because I told you about the fact that if you have an append call that's taking in recursive calls, you should check your wallet because something fishy is going on. So if I have inord, I should be able to do it better than n log n and n squared in the, or I should be able to do it better than n squared in the unbalanced case, because I'm effectively just doing a rev, right? I append to the front an L that might be like really, really long, essentially a list. So I want to implement T inord, which is a tail recursive inord. All right, can someone help me out here? How would I do this? What was that? Someone said something. What's my base case? I have it right out for you here. Oh, base PC. Yes. Who said that? Awesome. Okay. You're so unreasonably excited for this. No, it's fine. This is my entire incentive organization, so I'm perfectly fine with that. All right. So if I've got an accumulator, I pretty much just return it when I'm at the base case. I know it's harder to do it first, but it's also easier to think about if you fix yourself at returning the accumulator first off. Okay? So let's try to do it this way. Well, if I've got this, remember left root right. So I want to do the right, and then I want to put x on it, and then I want to put all the left stuff on. So what is my structure here? Well, I'm probably going to want to make a tail call to t inord, right? I'm going to conspicuously leave myself a lot of room here, okay, for an undiscovered reason. So somehow I want to get the in-order traversal of the right tree and then do stuff to it, right? Doesn't that just look like t inord of r? Does everyone follow? So like, all right, I want what's in intention L append x append r, basically x cons r, right? But I can only do it by making recursive calls to t inord. Well, if I can get the traversal of the right and I can get the traversal of the left, I might as well just use something that's like t inord L append, except I can't do that because it's tail recursive. I want to somehow augment my accumulator in a way that I can then do the stuff I need to do to it. So note that like what t inord does is t inord just adds to its accumulator, right? That's the idea behind like what rev is done. Well, every function we have had with an accumulator, it just does stuff to its accumulator. So what if we make the accumulator to t inord something that already has the information we need? What if we start from the right? So I'm going to write this, and let's figure it out, okay? I claim that this is going to be our right accumulator, okay? Our first accumulator. Because what we're going to do is we're going to get, this will evaluate by our recursive leap of faith to the recursive, to the in-order traversal of R. Then what do I want to do? I just want to cons x onto that. So let's actually do x cons onto that. So do you agree with me? This will be the traversal of x to R recursively, if I trust myself, if I trust inord. Don't just trust yourself, trust the code that trusts you, okay? This will just be x to R. And then shouldn't I just take that and then do the inner traversal of L appended to that? I effectively want, because the specification of inord, t inord, should be that it takes a tree, it gets the traversal, and it appends it to this, right? So isn't that what this is doing? I take the traversal of R, I append it to the accumulator, I put x on top of that, and I take the traversal of L and I append it onto that. In intention, if you look at the way I strung those words together, that looks like L append x cons R intentionally. That doesn't type check exactly, but that's the idea. Okay? So does this make sense to everyone that this should be our tail recursive inord function? We do the right and then the left. This will be a recurring theme, actually. Okay? It would be, we shouldn't do the right, left, and then the right because then we're going to reverse the tree. Okay? I'll leave that as an exercise to you. But thumbs up, thumbs down, people feel good about that. Cool, okay. Okay, well, I kind of want to do an analysis of this. I kind of want to do a work analysis of that. But here's something I notice. If I do W sub t inord, where n is the number of nodes in the tree, yada yada, I have two recursive calls, right? So it'll look similar in that it'll be 2 W sub t inord of, well, in a balanced tree situation, it'll be n over 2. So I'm gonna specify balanced. We're gonna do the first quadrant. N over 2 because L and R each have, yes. Yeah, that's fair. Okay, so let me put it this way. I think that it's improper to call it t inord in retrospect. Yeah, I would accept like improved inord. Let's call it I inord. All right, almost tail recursive. Let's say 8 at inord. All right, that's confusing. Let's just keep calling it t inord. I think you're correct though. It's not tail recursive. I didn't think about that. But because we are going to do this, and then we'll have to remember to do this stuff later, and this might be big. So yeah, totally fair. Good call actually. You get high choose for pointing out mistakes. Okay, so W sub t inord of n over 2 plus a constant factor because we just do this cons thing afterwards, right? And then we do a constant amount of work to combine the efforts. And then what you should find is that this is going to be, well, what does this look like? I'm going to get 2 times 2 W sub t inord. We're just going to go straight to solving. I don't have a whole lot of time, so I'm just going to kind of go through this kind of fast. So this is equal to 4 W sub t inord n over 4 plus 2 c sub 1 plus c sub 1. Okay, if you see the pattern, we should just keep doubling each time. double and give it to the next person, where the next person is this occurrence. And then n over 4 will just keep going. So we'll do this log times. And we're going to get 1 plus 2 plus ... Plus, what's my thing at the end? Well, I'm going to get roughly n of them, right? At the end, I'll have like n over 2 c sub 1. I'm kind of skipping over this, but you can verify the math for yourself later. C sub 1 plus c sub 0. And via our nice square math fact, this is going to be on the order of n, okay? Does anyone have philosophical opposition to this? Which is okay, it's a college campus. Okay, cool, yes. Here? Just the original 2 calls. Call it to this. Okay, let me justify that a bit. Yeah, okay, sorry. If I do this, that's 1 call. And then I have to do this call on L. But because I never touch ACK, the amount of stuff I have in this is not dependent on the size of my accumulator. It's only dependent on the size of the tree. And if I have a balanced tree, L and R must have n over 2. So I kind of glossed over that, but if you reason through it, you're going to get to this, okay? That follows from, I see some confused looks. This follows from the fact that I have to do this, and then I have to do this. I can't avoid that, okay? This will have implications for the span, but I do have to do 2 calls. Is everyone cool on that? And then if you're okay with 2 calls, you should be okay with the fact that my size metric is the size of the tree, and R and L are just n over 2, okay? So that's how we get this recurrence, and that's how we get a linear work. And then really fast, we're going to work through the literal rest of this matrix, okay? Because here's what I'm going to tell you. What is our parallelization opportunity here? How do we parallelize this? Yes? R? At the same time as T inord on L? I hear gasps of realization. We cannot. This is what we call a data dependency, okay? We have a dependency on T inord of L because this guy's got to wait. This call's got to wait on this to complete. Both T inord calls cannot be done at the same time here, okay? So I'm going to tell you that right now in the balance case for span, we're going to get exactly the same bound. And you can work this out yourself, and I'm not going to go through all of it, okay? This will be the same. Yeah. Well done. Good job. That's what I get for not reading. Comprehension. Yes. Yes. So we're going to get O of n here. And actually, I'm just going to cheat here and tell you that everything is going to be O of n. All right. I don't have time to work through this right now, but it is in the notes. Okay. We're going to have to move on though because we have some other stuff to talk about. In the last 15 minutes, we have the other. But it won't be difficult. Okay. The important thing I wanted to show you is that this has a data dependency. By seeing that you cannot parallelize, that's how we can get from here to here really fast, really easily. Okay. So realize that. All right. And then we're probably really far back. Yeah. So all this work is basically showing us that, and then we get this. Okay. What I wanted to get to was the comparison of inord versus quote T inord. Okay. Which is really just better inord, B inord, binord. All right. O of n in all cases versus inord, which is O of n on a good day, but it tends to fall behind. So this is kind of the interesting dichotomy here, where you have algorithms and you have better algorithms. And on the bad algorithms, sometimes you can have opportunities for parallelism. But you probably shouldn't have done that in the first place. So this is kind of a silly example where it's like, yeah, we showed that the span was better for inord, but we could have just not implemented it that way in the first place, right? Because it's n squared in the unbalanced case. It's n log n in even the work case if we don't have infinitely many processors. So why did we do that? Why do we even talk about it? So let's talk about an example where we can do parallelization and also it's like a reasonable algorithm, okay? I'm going to move on from this, okay? We're going to be talking about, any questions? Okay. We're going to be moving on from this and we're going to talk about one of the most classic problems in computer science other than helping your parents with their printer. It's going to be sorting a list of integers because it's a really kind of classic thing we want to be able to do, okay? Who can name some sorting techniques? What are some sorting algorithms we know of? So I'm gonna say rogue sort? Well, okay, all right, I didn't, okay. This is not 98 150 esoteric sorting algorithms, okay? let's stick to the established. So we've got some stuff like someone said bogus sort, I'm pretty sure. But we've got like, there are things like insertion sort, there's things like selection sort, there's something called merge sort, which I've alluded to. But we're gonna have some good sorting algorithms and some bad, okay? So let's try to look at one that's called insertion sort first. Here's the idea behind insertion sort, okay? We're gonna take a list that's already sorted. And if you try to put an element, any element, into a list that's already sorted, so like 1, 2, 3, 4, and I want to put like 2 again, okay, into this, well, it's kind of easy, right? Because I just like kind of go through until eventually, you know, the next element is greater than it, and then I just put it there, right? So we're going to implement insertion sort real fast, okay? But that's the idea of the algorithm. Is anyone confused? We're just going to try it. Well, basically, we're going to recursively sort and then insert the first element, okay? But to do that, we're going to need a helper. We're going to need that helper that inserts into the already sorted list. So that's called ins, okay? It takes in an already sorted list, and it takes in an element, and then it just puts the x into wherever it should go in the already sorted list, okay? Let's do it here. Let's do ins of x, int, and then nil of type int list. What is this? X, the list of x, right? Yeah, whatever. And then ins of x, and then y cons y's. Well, I have two cases here, right? If x compares to y, right? It might be less, it might be greater, all right? So let's do both. If x is less than y, what should I do? That means I haven't reached the right point yet, yeah. X cons y's, so let's try it. But if I insert 1 into, actually, yeah, I like that, okay, cool. So we're gonna see this, yes. X cons y's, yes. I wanted to check that for myself because something I had trouble thinking. X cons y's because it's less. And then if we invert, like, get into like 1, 2, 3, 4, and we get 2, well, this is greater than, this is greater than, this is less than. So we're gonna get here. And then if I'm greater or equal to, that means I haven't found my right place yet. Because if 2 is greater than 1, I haven't found the right place yet. So I want to keep going. So we're gonna peel off the first element, and then do insert x into the rest, right? Okay. Is everyone confused on whether or not this should be linear and such, or whether or not this is insertion? I'm not going to justify this as linear, but know that it is. And this is the insertion function we're going to use. So if I have my insertion function, I can implement insort, where the specification is written right here. Yes. Did I reverse it? No, I didn't. Oh, sorry. What did I do? Sorry. Wait. Yeah, I was saying that's the typo. Yeah, this is wrong. Yeah, this is wrong. Sorry. It's supposed to be, that's not x twice. Don't do that. Cool. Okay. But we keep inserting the x. Yeah, okay. Yeah. Cool. Okay, cool. Yeah, that's definitely a typo. Okay. But let's just say that we're inserting a list which is like this. We're trying to sort this list via insertion sort. I'm going to tell you this is just an empty list, and then this is. Okay. Recursively sort the rest, and then insert the first element, right? If I can already sort the rest and then I insert the last one, I'm done. So doesn't that just look like this? Insertion sort the rest, get an already sorted list, and then insert the first element. If you think conceptually about it, you trust the recursive leap of faith, you trust your preconditions, this is just how we do it, okay? Cool. Very, very terse, all right? If you're confused, we can think about that later because we got to get to merge sort, all right? This is the big one. Okay, because I promised you I'd be able to do this. So this is very simple. This is still there, but that's fine. That is O of 1, O of n, and then so we're going to get this. I'm not going to write all this out, but basically the point is that if I do insort, I'm going to get a call on n minus 1, which is the rest of the list, x's, and then I'm going to do insert on a list of length n minus 1, right? Because the result of insort is going to be the same length as the input list, which is x's. So I'll get this recurrence, which solves out to n squared. This shouldn't be surprising to you because this is such a simple sorting algorithm, all the simple sorting algorithms are always quadratic. Okay, so this is how it goes. So we're going to try and do better than quadratic because quadratic is functional speak for bad. Okay, it's computer science speak for bad. So let's try to avoid that if we can. All right. And you can follow that through on the slides later if you want to see how it's n squared. And I'll also say there's no span we can do because we can't really parallelize anything here. Like there's a data dependency. I have to insort and then I have to insert. So if I want to do this, I want to be able to find a sort where I have some parallel opportunity. That's going to be called merge sort. All right. Someone else invented that. Someone smart. All right. It doesn't matter. So what we're going to do is the idea behind merge sort is we have a list, x1 through xn. What we do is we cleave the list in half. Okay. Doesn't matter how. Doesn't even need to be like this necessarily. But we cleave the list in half, and then we turn it into two halves. And then we sort the two halves. Okay. So that now we have a sorted list L1 and a sorted list L2. And if you think about it, if I have like 1, 3, 5, and I've got 2, 4, 6, right, where these are two sorted lists, it's very easy to take these and turn them into a single sorted list. How? Because I just like, oh, this one's less, so I take it. So I have 1, and now like that's gone. And now I have, oh, this is less, so let me take that. That's 2, and that's gone. And that's we basically like shuffle them together. It's like shuffling cards almost. Okay. The idea behind the algorithm is we're going to split, sort, merge. That's exactly the idea behind the algorithm, and we'll see it in code right now. I think I'm going to talk through it and not write it on the board here. Okay. Actually, no, no, I'm not going to do that. Okay. So let's try it out. But I will omit. No. So let's talk about split, and let me tell you the I realize I'm going a little fast, but I kind of have to do this. Okay. So this is going to be our specification, okay? Split takes in a list, turns it into two lists of approximately the same length, okay? I'm going to give you this for free, which is that if I do it on a singleton or I do it on nil, I'm going to get this. Sorry. If I split the empty list, I get two empty lists. If I split the singleton, I'm going to put it wherever. I don't really care, okay? Okay, and then the really easy way to implement this is we're going to just do the bulk of the work in this case, x's. Okay, I'm going to peel off the first two things, and then I'm just going to split this. Right, I'm going to split x's. So let val a comma b equals split x's. So remember, this is how we pattern match on the result of a tuple. Where the result is a tuple, x cons a, y cons b. And if I can split this, and I'm holding two elements, can't I just put it one here and one here, and now I have roughly equivalent elements? You could do this proof by induction if you wanted. You could prove, oh, the result of split is roughly the same number of elements. I'll promise you that it'll be off by 1 at maximum. Yeah. What would be this thing? Yes, so when I said this, where I cleave it down the middle, that's not exactly what we're doing. We're actually going to be shuffling them. But the key is, so I actually kind of prefaced this where I said, like, you can kind of do something like that. I don't care. I just want it to be halved. I just want roughly half pairs because I'm going to sort it anyways. So this happens to be the most efficient way for me to do that. Otherwise, I'd have to like do some nonsense with indices. And who wants to do that? This is the functional way. This is how we split a list. All right, but good observation that yes, it would be like A, B, A, B, A, B, and eventually it would be down to like A or something, okay? That's split for you. Okay, if you believe me, it'll be this. And then next I want merge, okay? I want to be able to merge two elements together real fast. So it's not this, right? Okay, so let's do it. If I merge two elements, that's fine. I'm gonna have two cases. One where the left list is empty, and I've got x's. I'm going to write the type annotations out. It's fine. I'm going to write this and then explain it, okay? Okay, if I have an empty list on the left or the right, if I want to merge an empty list with a list, it's just going to be the result of that list, right? That should be easy to reason through. The interesting case is now this one, which I claimed to you was the only case left. Okay, if I have x cons x's, y cons y's. I have two cases here. Either I've got like 1 comma da da da, or I've got like 2 comma da da da, right? But these are already sorted, is the idea, okay? I'm going to precondition require that these two things are already sorted, and I'm trying to merge them together. Well, I only have two cases then, right? If x is less than y and if x is not. And if x is the lesser element, I want it first, right? So I'm going to do this. I'm going to do merge, or x cons, merge x's, y cons x, y's. I'm going to put y back on, because I want to be able to do the next comparison, okay? I don't know whether or not y is less than or greater than the next element in x's, okay? Otherwise, if y is the lesser one, or equal, that's fine as well. Y cons merge x cons x's, y's. Okay? Does this make sense to people as to why that should be the case? I take one off, and then I redo it, where now I've uncovered a 3. Okay? And then so I put the 1 here, and then I see the 2. Oh, okay, I got a 2 now, but now suppose it's like 3 again. Now I don't care, so I'm going to do this one. Yes, so there was a question. Oh, it's on the screen. Yes, it is. Sorry. Does everyone believe me this is merge? Okay. Let's write merge sort, and let's do it with extreme prejudice. So remember, the idea behind merge sort is split, sort, merge. And actually, I'm going to claim to you that this is going to be pretty much exactly where our code reads. Let's call it M sort. So this is M sort of type intlist to intlist. And I take it an int list and I get back an int list. Okay? If I'm sorting the empty list, I get the empty list. I'm going to conspicuously leave myself a space here for no reason whatsoever. Okay? Let's just call it L. All right. If I want to sort L, split, sort, merge. So let me let A and B be equal to split on L. And then let me sort L, and then let me sort A and then sort B. So M sort A, M sort B are just going to chill here for a second. And then I want to merge these two together. Well, it just so happens to be they were already here in the right spatial position on the board for me to do this. Split, sort, merge. This is merge sort. I'm going to tell you right now for free that this is not going to work. This is actually going to loop forever. Okay? It turns out that what you need to do is this. The reason for this is because if you pass in, if you went into this with the singleton case, this would be a singleton, right? If you pass in the singleton here, split of the singleton returns. It's not split, but this would be a singleton, and then you'd call merge sort on a singleton yet again, and then you'd loop. You'd loop forever. So the fact that split has like 2 base cases kind of means that merge sort needs to have 2 base cases too. But if you believe me, this is merge sort. And then it should almost read like pseudocode, I wanted to say, but this is it. That's merge sort in SML, 20 lines generously spaced. Okay. There is a section after this where we do a whole span analysis. And what we're going to find is we're going to find that the span is going to be linear. We're going to get linear span and n log n work. And that's the power of parallelism. We're going to be able to do a linear time sort. Someone might tell you linear time sort is impossible. Nah, you just need infinitely many processors. Okay? All right? But that's merge sort. This is, I regret I didn't get to spend more time on this. I think this is one of the coolest things. Who took 122? Does anyone remember implementing merge sort in 122? Do you remember the pain? I do, all right? 5 years later, all right? It was terrible. This is it. That's it. And that's the lecture.